we have a sequence phi of n. Looks like a function, but in fact it's can be viewed as sequence, so larger than 0, increasingly approach positive infinity. And so that also an sum, infinite sum, approaching S, then show that the sum of ak times phi k equals little o of phi of n. Little o can be viewed as a sequence approaching 0. Doesn't have to be unique. In other words, this sum, if divided phi of n, will approach 0. In other words, this is some sequence approaching 0 at a higher speed than phi of n. And this result was provided by Kronecker. And first, we're going to prove this lemma provided by Abel. And the partial sum, this partial sum can be written as this result plus this partial sum. So in other words, this is like a discrete version of integration by parts. So ak minus 1 can be viewed as dv. bk can be viewed as u. So u times dv equals, this can be viewed as uv, evaluated from n up to n, right? So this is dv, v is just a, right? And this is du. This can be viewed as v times du, right? This discrete version. And it's particularly useful in dealing with the convergence of infinite sum of the form of product of two terms, like ak times bk. So first, this lemma. Right? This lemma. K goes from m up to n. ak minus ak minus 1 times bk. Of course, I'm going to distribute ak, bk to ak minus 1, split them up. So that will be equal to k, go from m to n, ak times bk minus sum from m to n, ak minus 1 times bk. Now, this time I'm going to re-index it. Right? I'm going to change this, because in order to reach bk minus 1, right? Bk plus 1, I should re-index this k into k plus 1. Okay. So that's equal to k goes from m to n, ak bk minus, if I re-index, for example, k minus 1 becomes k, then k becomes k plus 1, right? The dummy index doesn't really matter. So k, the first term, k equal to m minus 1. So m minus 1. Right, last term is n minus 1. N minus 1. Right, these two things are equal. So again, this time we have ak, bk plus 1. But right now we don't have exactly the same number, right? So maybe I can separate this last term from this sum. Separate the first term from this sum. So last term of this sum is a n bn. First term of this sum is minus a n minus 1 times b m. And then we can have combine the partial sum. K goes from m all the way up to n minus 1. Right? Because last term is separated. Here, the first term is separated. Right? So combine ak, bk plus 1. Extract ak. I have bk minus bk plus 1. And that's exactly the desired result. Right? Then I'm gonna, in order to prove this, I'm gonna let A1 plus all the way up to AK equals SK. Right. So in other words, if AN approaches S, I say, so AN plus all the way up to AN, SN, meaning SN approaching S. Right. And also, I'm going to let AK equals SK minus S. Right. So therefore, AN is equal to SN minus S. So therefore, this left-hand side, right? K goes from, I'm also gonna let M equal to 1. Right? K goes from 1 all the way up to N. AK minus 1. What is that? SK minus S is gone. SK minus SK minus 1 times BK. BK, I'm going to use phi of K. And that's should be equal to AN, BN, SN minus S times BN is phi n minus A naught, M equal to 1, A naught. What's A naught? Is S naught minus S. What's S naught? S naught doesn't have any meaning. S1 has meaning. Let me just define S naught to be 0. So that way, A naught is minus S. So therefore this has meaning. So minus S plus S times B1. Yes. Then plus sum from 1 to n minus 1 of AK is SK minus S. Times BK plus, like I said, BK is phi of K minus phi of K plus 1. Maybe I want to, because phi of n is increasingly approaching positive infinity. Maybe I should switch those two just to make sure it's positive. So I say it's this becomes minus phi of K plus 1 minus phi of K. Now I've reached this result equal to that. So I'm trying to prove that this is equal to little o of phi of n, but this AK is in fact SK minus 1, because the terms from A1 up to AK minus 1 all cancelled out, right? So therefore this SK minus 1 is in fact AK, right? AK times phi of K. K goes from 1 to n. So in fact, all I need to show is that this divided by that, is it approaching 0, right? So K goes from 1 to n. ak times phi of k divided by phi of n, right, is it approaching 0? Right, in other words, I want to see if this, in other words, this divided by Sn minus S times phi of n plus S times B1 minus k equals 1 to n minus 1 of Sk minus S times phi of k plus 1 minus phi of k divided by phi of n. Is it approaching 0? In other words, if I divide everything here, that's included in the numerator. So everything divided by this part, right? So this part will be gone. So in other words, I want to find out if Sn minus S plus Sb1 over phi of n and minus over phi of n sum from 1 to n minus 1 Sk minus S times phi of k plus 1 minus phi of k. Is the whole thing approaching 0? So if we look at this part, no problem. Definitely approaching 0. This part, no problem. Because B1 times S is just constant, right? Phi n approaching positive infinity, no problem. The question is this part. Is this part approaching 0? So maybe just can be written into two parts, of course. First, I'm going to start from 1 all the way up to capital N. Right. One up to capital N plus from capital N plus 1 up to little n minus 1, right? The same thing, over phi of n. Now, so this capital N, what I mean by that is, as long as for any given epsilon that's small enough, positive epsilon, I can always find because it says Sn approaching S, right? So first I split into this finite sum. So this n, capital N is fixed. And so that for this sum, for this part, the difference between Sk minus S should be smaller than some epsilon. So first, let me just first, S maximum S1 minus S, S2 minus S, S capital N minus S. There is a maximum, because there are finitely many terms, there's a maximum one. So to make sure it's positive, maybe I plus 1 and denote it as capital M, right? So that if I put an absolute value of this k goes from 1 to capital N. This absolute value should be, can it be small enough? Right. First of all, it's no larger than, put the absolute value inside. Right? K goes from 1 up to capital N. Put the absolute value inside. Phi of n already positive, right? Don't worry. And absolute value of sk minus s times absolute value of, don't need absolute value of the phi of k plus 1 minus phi of k, because it's increasing, right? Given to be increasing. So this is no larger than replace sk minus s with the maximum of this, right? Plus 1, capital M, right? So further loosened. Take M out. Sigma k goes from 1 to capital N of, perhaps also take out phi of n, right? And what I'm left with is just phi of k plus 1 minus phi of k. And so this sum is easy, should be easy to work out. So equal to m over phi of n times the first term phi of 2 minus phi of 1 plus phi of 3 minus phi of 2 plus phi of n plus 1 minus phi of n. Okay. So phi of 2 minus phi of 2 cancelled out. And so the pattern is always the two pairs. Right? The first term, first pair cancelled with the second term of second pair. So phi of 3 should be cancelled with the next negative phi of 3 somewhere. Phi of 1 stays. And negative phi of n will be cancelled out with previous one, somewhere prior to this one. And this one will stay. Because it has no more term afterwards, right? This one will stay. So will this one. And so the first sum from k up to capital N is no larger than this expression. But capital N is fixed, right? Capital N is also fixed, and so is this one. So maybe just write this term as m naught, right? M naught over phi of n, right? But phi of n approaching positive infinity, so 1 over phi of n approaching 0. So in other words, there must be a capital N where as long as n is great enough, big enough, this can be smaller than perhaps, let's just say phi of n can be smaller than 1 over phi of n can be smaller than 4 times m naught epsilon, right? This is definitely doable. Right, as long as little n is bigger than capital N1. So the first sum over phi of n, absolute value can be small enough. So the question is next part, this part, right? So absolute value of, let's say, sum from capital N plus 1 up to little n minus 1. Absolute value over phi of n. Right, first of all, smaller than or equal to, put the absolute value inside, right? So inside here, phi of n sum from n plus 1, n minus 1, absolute sk minus s times phi of k plus 1 minus phi of k. Right, this part I don't need the absolute value because it's already positive, right? Increasing. So again, this part replaced by, like I said, Sn, right, the sum or partial sum equal to approaching S, right, Sn, A1 plus all the way up to An. So which means as long as n is big enough, Sn minus S should be small enough, smaller than epsilon over 4. Right, because right now I'm starting from capital N plus 1, where capital N is big enough, right? Bigger than capital N. So this can be replaced by epsilon over 4. Epsilon over 4 times phi over sum from n plus 1, n minus 1, phi k plus 1 minus phi of k. Right. So can this be bounded? If it can be bounded, then I'm fine. Epsilon over 4 can be small enough. So first, let's work out this finite sum, right? So that is equal to first term phi of n plus 2 minus phi of capital N plus 1 plus phi of n plus 2, n plus 3 minus phi of n plus 2. All the way phi of n minus 1 n plus 1, phi of n minus phi of n minus 1. Right. So again, so phi of n plus 2 minus phi of n plus 2. Right. Same pattern. Right. First term of the previous pair cancelled with the last term of the next pair. So this will cancel out with some term afterwards. This term stays, and this term will cancel out with the previous first term, the previous pair, right? This is the term, last term of this pair, previous pair, first term cancel with this one, and this one I think will stay because this one is supposed to cancel out with the last term of the next pair, but there's no next pair, so this one stays. Right, so with this one. And so this term can actually be written as epsilon over 4 times phi of n. This is phi of n minus phi of capital N plus 1. Right? And so, like I said, as long as this part can be bounded, then we're fine. Right? So, yes. So actually, phi of n is definitely greater than phi of n plus 1. It's increasing, right? So this is positive, minus some positive. So if we don't do the minus, somehow it can be bigger, right? So we loosened. So no larger than this one, right? And so phi cancelled out, right? So really can be smaller than epsilon over 4, can be small enough. And so that if we want to be more rigorous, like I mentioned, right? This one approaching 0. as long as n is big enough. Right? Maybe I can claim that as long as n is bigger than capital N2, this can be smaller than this can be smaller than epsilon over 4. Right? Also, this one can be also smaller than epsilon over 4, right? This is also approaching 0 as long as n is bigger than capital N3, right? So altogether, epsilon over 4, epsilon over 4, epsilon over 4, right? That's this partial sum over phi of n, right? And also this sum over phi of n smaller than epsilon over 4 as well. So altogether, this is smaller than epsilon over 2, right? Epsilon over 4, epsilon over 2, epsilon over 2, altogether smaller than epsilon, as long as n is bigger than capital N1, capital N2, capital N3. And you say, as long as n is bigger than the maximum of all those capital N, can be really smaller than epsilon. All right, so like I said, I'm done proving. Previously, I say, as long as we can prove this divided by phi of n approaching 0, then we're done, right? And so eventually we've concluded that as long as we can prove this can be approaching 0, then we're done. And so it's really true.